Okay, Jason. I've gone over these problems you asked me to look at. I'm gonna send them to you. Give you a link, and then we can go over these on Tuesday. So the first one you want to know is 28, and so it says a student mixes dilute silver nitrate with excess sodium chloride to form sodium chloride as a precipitate S, as represented by the net ionic equation above. Which of the diagrams best represents the ions that are present in significant concentrations? It gives you KSP. Really don't need to know this a whole lot, except the only thing you have to know is that what this tells you is that there's not very much that well, just about all of the silver chloride it has become a solid. So the -10, so this amount here, this equation is how much is soluble. So it's a rough, it's a fairly close to approximation. Basically, it says that there's 1.8 times 10 to the minus 10th moles per liter of this ion that's present, which is a very, very, very small amount. So most of it is going to be a precipitate. Okay, so look at this exponent -10 here. So we have this pile of silver nitrate in each one of the four boxes. Okay, so the reaction is, so if you think about the reaction is is actually going to be Ag uh, NO3 plus sodium chloride. Okay, and both of these are aqueous, and then you're going to end up with silver chloride plus, which is a solid. The sodium and the nitrate are both going to be soluble. And the key word here is excess. Okay, so that means not all the chloride is going to combine with the silver chloride, and so there's also going to be some chloride there. Okay, so you're going to have this ion, and this ion that are soluble, and then this guy that's not. So if we look at the four boxes, the first box A just has these two guys. This B is totally wrong because it doesn't have sodium or nitrate in it. C looks like it might be our choice because it has the nitrate, it has the chloride, and it has sodium. So this looks like our guy. So let's just check out D, make sure. And D has sodium, nitrate. The problem with this one is it's also got the silver, which there is a small amount in it, okay? But it says significant concentrations, okay? So pretty much all of the silver nitrate has precipitated out. Okay, so that's problem number one, 28. We'll go on to the next one and so forth. Okay, so this problem has to do with 29 through 33, and it deals with this reaction here, and this reaction is going to go to equilibrium. It says PCl5 decomposes to PCl3, Cl2 gas are all the same state, so you don't have to worry about any heterogeneous types of effects. The pure sample starts out with 1 liter of the PlCl5, and the initial pressure is 1 atmosphere. We don't have to worry about this. If it was a concentration problem, we would deal with it, but this is a pressure problem. Okay, the temperature is held constant. That's good. All right, so we don't have to worry about a change in temperature, which would affect pressure. And so we have, this is our beginning, and this is our end. Okay, so we're going to be using our ice table in a couple minutes, but first of all, there's a couple concept problems here. Which is number 29. Which of the following is most likely to cause increase in pressure observed in the container as the reaction reaches equilibrium. Well, the reason why the pressure goes up is because you're creating product. Okay. All right. All right. Uh, and so some of the reactant is turned into product. So that means you have more gas particles. Okay. So simply that's what you should be looking for. All right. If you look at the four different answers, a decrease in strength of intermolecular tracks that's irrelevant. Okay. I mean, we don't know anything about the. It's basically you're going from this to these three things. All right. And the only one that really fits that is this guy right here. Because the more particles you have, the more pressure you'll have. Okay. Whoops, sorry. It should be this one right here. C. An increased number of molecules, which increases the frequency of collisions with the wall of the container. So this is it. Okay. D would be a temperature effect because speed is related to temperature. Okay, so it's C. So the more you have more gas particles, which cause more collisions. Straightforward theory, the kinetic theory of gases. Okay, problem number 30, which relates to the same equation. As the reaction progresses towards equilibrium, the rate of the forward reaction. So the what one of the definitions of equilibrium is the rate of the forward reaction is equal to the rate of the reverse reaction. So increases, so let's look at each one. Increase it until it becomes the same as the reverse reaction at equilibrium. That looks like it's pretty good, okay? Stays constant before and after. No, that's not fine. So the rate's going to increase, okay, as the forward reaction is going to increase until it reaches this reverse reaction. Decrease it to become constant non-zero rate at equilibrium, decreases to become zero. No, this is the one that works because the definition of at equilibrium is the rate forward equals the rate reverse. Okay, problem number 31. So we have our equation. Okay, so this says it goes in completion. That means there's none of this left over. So you start at 1 mole, and then if you have 1 mole of this, it will produce 1 mole of this and 1 mole of this. Okay, we're assuming that the number of moles is related to the amount of pressure. So if you have one, it's not. I mean, it's if this started out with 1 atmosphere, this would have to be 0 atmosphere of this at the end, 1 atmosphere here, and 1 atmosphere here, or 2 atmospheres. Okay. So basically, it's just stoichiometry. If there would have been like a 1 here, a 2 here, and a 2 here, then you would have ended up with 4. Okay. In fact, it doesn't even matter what this is over here. What it is that you have this. All right. Okay. So, all right. So all of our reactant turned into a product, and it's just a stoichiometry relationship. One of these plus one of these, so you end up with 2 atmospheres. Okay, so which of the following statements about Kp is correct? All right, is Kp greater than 1, less than 1, and Kp equal to 1? Well, we can actually figure it out. So we're going to use the ice table here. So we have our reactant going to our products. Okay, whoops, that should be just Cl2. Sorry about that. Okay, and then let's make our ice table. Sorry about the lines. Okay, so initial change in equilibrium. Okay, All right, so we started out with 1 here, 0, and 0. And then what happened to get equilibrium, this had to change by some x, this increased by some x, because the coefficient is 1. If it was 2, then you would have had 2x here, then 2 here. And then their final concentration for each one at equilibrium has to be, okay. All right, we know that the total pressure when we, in the previous problem, the previous statements, it tells us the, after it reaches equilibrium, the pressure is 1.4. So the sum of these three pressures has to equal 1.4. So we're not doing anything with equilibrium right now. We're just finding out how much pressure is in, does each one of the species contribute. Okay, so this has to be 1.4 atmospheres, okay? All right, and then we do some simple math, okay? And then we just combine terms and such. We get 1 plus x equals 1.4, and finally x equals 0.4. Okay, so so now what we can do is actually figure out what Kp is, because Kp is equal to product over reactant, so it's going to be our PCl3 pressure times our Cl2 pressure, that's our product, all over our reactants pressure. Okay, so just plug it in. So we get 1 minus 0.4, so this is 0.6. Okay, and these are 0.4. Okay, so we're going to get 0.4, so it's Kp equals 0.4 times 0.4 all divided by 0.6. Okay, when you do that, the answer ends up being 0.27. Okay, so that means that the Kp is less than 1. Now, so let's think about this a little bit more. If Kp is less than 1, that means the reaction favors the reactant. Okay. If it's greater than 1, then the reaction will favor the product. So if we okay, so this reaction will always drive towards the reactant. Okay, so okay, so that's going to relate to the next problem. Okay, so so this asks you, so if you start out, here's our equation. Okay, so it's at equilibrium. That's what it says here. Okay, and then what we're going to do is we're going to add more of this. Okay, now according to the Le Chatelier's principle, what's going to happen is that this is going to drive the reaction back this way. Okay, so what you're going to get is you're going to get an initial increase of your Cl2, and then it's going to decrease to have everything create a new, well, keep the same equilibrium, but change the amounts to keep that equilibrium the same. So everything's going to increase because you add Cl2, so that's going to increase, but it's going to go down because some of it's going to turn into these two guys. Okay, so initially it's going to go up. Okay, and then what's going to happen is it's going to go down, but it's going to be higher than where it started. Okay, and also Okay, so your curve should look something like this. Okay, so here's your initial Cl2. Okay, you add the Cl2, it goes up, and then what happens is that some of it goes to form the other two species. All right, but not all of it. Some of it will say Cl2. All right, so let's look at the four different graphs. Okay, this definitely is not it because it says that my initial Cl2 is 0. This looks pretty good here. It looks like the infected graph I just drew. Okay, this one says your CL2 drops down to lower than it even started. Okay, I don't know why that would be. Okay, that means is that uh, it wouldn't. You've added the CL2. It doesn't mean it's going to decrease completely. Some of it's going to stay as it is. And then finally, this one, okay, it goes up. All right. Uh, and then it reaches some point here. Uh, this looks like it goes up gradually. We're saying is that you're adding it and then you get an immediate change. Okay. All right. So this one says is that uh, somehow it doesn't detect that there's the Cl2. All right. So as soon as you put it in, it should be detectable. All right. It's not. So that amount you add is detectable. This looks like the Cl2 that you add is not even detectable. All right. So that's definitely this one here. Okay, so this has to do problem 48 through 52. All right, so we have four different acids. Here they are. And we got questions dealing with those. So let's look at our data before we even go into the problems here. So the four acids: hydrochloric acid, lactic, propionic, and chlorous acid. Now, hopefully you know a little bit about names. If you've heard of acid, you might have an idea if it's strong or weak or whatever. Um, Hydrochloric acid is a strong acid. Lactic and propionic are weak organic acids, and chlorous is a lot like hydrochloric acid, but it's weaker. One way you kind of tell is it's us. Us acids are weaker than ic acids. So I would say this is my strong acid. This might be my second, and these guys are my third and fourth. All right. So right off, if I look at the table, I can guess that this is probably going to be my HCl. This is probably my chlorous acid, and one of these are going to be my propionic and lactic acid. All right. All right. So the first question says, which acid has the smallest Ka? All right. So if you think about this, so Ka is, so let's just look at different Ka. So let's say your Ka is 10 to the minus 10th, or another Ka is 10 to the minus third. All right. And so, we have pH. So is there a relationship between pH and Ka? Yes, there is. Okay. So, and we're just going to use a general rule of thumb here. So we know that pH the is the negative log of the H3O plus. Now it turns out that pKa is a lot like pH. Okay, so if I take a look at these two guys here and figure out their pKa, so you could see that this guy here is this guy has a smaller Ka than this one. All right. So how can that relate to pH? All right. So let's change these to pay like their pH. All right. So it's not exact, but it's a good useful term. So we'll put in quotation here is that the pH. Now this is not going to be exact, but at least give us an idea. Is that this pH is going to be 10. Okay, and the other pH is going to be 3. Okay, I know that this guy here is smaller, and therefore it has a larger pH. Okay, so the question says I'm going to look for a small Ka. I should be looking for a high pH. Okay, all right. So which one of these four have the highest pH? Acid 1. Okay, I hope you get that. This is that the way that I think about it is Ka, and this is just a quick way to figure out. This is that I treat Ka like pH. So I know that if I have a small Ka, okay, that's like having a high pH. Okay, just remember what the pH formula is. Okay, pH formula is going to be 10 to the minus what pH. Okay, and if this pH is a large number, okay, that means the H plus is going to be small. It's the same idea here. If the Ka is small, the pKa or the pH is going to be large. Okay. All right. So, okay. Second problem. Which of the four acids listed in the table is hydrochloric acid? All right. We decided that at the very beginning. It's probably going to be number 2. Okay. Before we go on, I just want to make sure you get this. Okay. Is that if you want to know Ka, kind of treat it like pH, right? So if you have a high Ka or low Ka, that means you're going to have a high pH. Think of like base. So this kind of says is which one of these is kind of more basic, all right? Has a higher small Ka's means more basic. Okay, so this is going to be a trick problem. If equal volumes of four acids have concentrations of 0.5 molar and are titrated with a strong base, which requires the greatest amount of base to reach the equivalence point. Okay, the key thing is right here, volume, concentration. So let's say each one of them, you take 20 mils. Let's turn liters. So each one, let's say you take 0.2 liters. Okay, and the molarity is 0.5. So it's 0.5 molarity. Okay, the amount of moles is going to be 0.01 moles. Okay, so each one of these guys, we're going to titrate 0.01 moles of each one of these. Okay, well, a mole of acid is a mole of acid. All right, so it's going to each one of them is going to require the same amount of base. It says you're adding some concentration of 0.5 molar. That means they're all going to have the same amount of acid. Okay, in this case, I made it 0.01. Therefore, they're all going to be the same. So it's going to be the same. All right. So it's kind of a trick question. You don't have to know anything about the pK or anything like that, because what you're doing is you're getting rid of all the acid. You're not having it go to equilibrium, which pKa is related to. Okay, so all right, so that's it with this one. So just pay attention to it. Is that how this is written? Okay, it's just saying if you add some amount at some concentration of each acid, they all exactly the same, then they are then that's how many moles you have acid, and that's how much it's going to be titrated. So that's how much base you're going to add. Okay, pH of these so forth. So we're going to look at acid number 1, and what we want to know is which one of these is most prevalent at an equilibrium, and this is our initial, well, at the concentration of our acid. So here's the thing. So we start having acid, and it goes to its conjugate base. Okay, plus H plus. Okay, so uh, so we're looking at A. So this is a very weak acid, so that means most of the, see these numbers are high, okay, which means it's a weak acid. That means most of the acid when you at equilibrium is going to be acid, all right? Very low of it, very small of it will be base or H3O plus or H plus. So let's look at our answers here. So OH, okay. Uh, this is a base, okay. And it's not even in this equation, but we can figure it out. But we know that we're going to have, it's mostly going to be acid. All right, H3O plus is this term over here. This term is going to be much greater than either one of these go over here. Acid 1, yep, that's probably it, because here it is. And the conjugate base is this guy here, right? And we said that's not it. So the key thing here is we know that, if you have a high pH, that means the pKa, or so that you have high pH. So high pH, okay, means you're going to have a high pKa, which means you're going to have a low Ka. Okay, that means is that not much. So Ka is the relationship of our product over our reactant. So Ka is B times the H plus all over A, our acid. And this number has to be really low. And the way that this number can be really low is that if this is high. Okay, so that's how I determined it, all right? Okay, so you have, so I know this guy is a weak acid because I can see the pHs are high. Okay, so if the pH is high, the pKa is high, and that means a low has a low Ka. And what is Ka? It's the relationship between the base and H plus or H3O plus over the amount of acid divided by the amount of acid. And the only way that this term can be, this whole thing could be low, well, it could be low different ways, but one way it can be low is that if this number is high. All right, and so we got that. Okay, so last problem relating to this situation here. 25 mils of 1 molar acid 1 is mixed with 25 mils of 0.5 molar NaOH. Okay, and then after you do that, you add a few drops of nitric acid. So let's look what happens. So let's say you have your acid, and what I'm going to do is I'm going to go H, and then okay. Sorry. So it's going to be H plus with the conjugate base there, and that's what acid is when it starts out. It has an associated, right? And then after it reaches equilibrium, you will have this. Okay. Right. And then what we're going to do is we're going to add some sodium hydroxide. Okay, so what's going to happen is the sodium hydroxide is going to combine with the OH, and you're going to create more conjugate base. Okay, so now you have sort of more conjugate base. All right. So now, what happens when you add the nitric acid? Okay, so nitric acid is a strong acid. Okay, so H plus will come off. What is it going to do? Well, initially you would think is that it would increase the amount of H plus. Okay, but what happens is that H plus is going to combine with a conjugate base to drive the reaction back in the reverse reaction. So you can think of a Chatelier's principle here. You added more H plus, it's going to drive the reaction back to the left. Okay, and also we have to think about is that the H plus is actually being absorbed by the conjugate base here. All right. Okay. Uh, the OH, it only was involved with the very first step, work combining with the H plus of the acid. All right. So so you have more B conjugate base, which is going to react with the H of the acid. So let's see which one of these four answers relate to that. Okay, pH of the mixture increases sharply because HNO3 is a strong acid. So this is wrong. I mean, it's possible if you didn't add the NaOH and you added the HNO3, it should become more acidic, and if it's more acidic, the pH should actually go down. So it's not A at all. So B is actually that situation. Okay, but the key thing was is that uh, we added the NaOH, which is going to have an effect on the system. So if you just added the nitric acid, therefore it would have created more H plus, which would increase the amount of acid, which decreases the pH. Remember, increase in acidity is inverse to pH. C. The pH of the mixture stays about the same because the conjugate base of the acid reacts with the added H3O plus. And that's what we just said, okay? So you add more H3O plus, which the H3O plus comes from this H right here. It's going to combine because we have more conjugate base, and therefore the pH is going to stay about the same. So it's not, this extra H is not going to increase the acidity. Okay, so we're more than sure, it's pretty sure it's C, but let's look at D. The pH of the mixture stays about the same, yes, because the OH ion combines with the added. No, okay, the initial OH minus reacted with the H plus of the acid, okay. All right, so hopefully you can see how that works. Okay, two more problems. Okay, number 55. So the table above gives you Kas for 4 weak acids. Uh, you have the following pairs of chemical species when combined equal amounts results in a buffer pH closest to 7.5. So there's different things. Let's look at our data before we go try to determine our answer here to try to distill some stuff from it. So let's look at the 4 different samples. Okay, so in each one of these samples, you have your acid and you have your conjugate base. Okay, so so you have A going to conjugate base plus H plus, and so you this and this. Okay, and these guys are going to be in equal amounts. Okay, and when that happens, that means when the acid and the base are equal amounts, the pKa is equal to the pH. All right. So we know that pKa has got to equal to pH. All right. And so what is Ka? All right. pKa. Well, pKa is equal to the minus log of Ka. All right. So we have the Ka's here. And we can just plug them in here. And then they should equal, that should equal the pH. Okay, I'm going to do a real quick, I'm not going to use my calculator. I'm just going to come up with a quick answer right away. And it's because I think I mean, you can try to, you can use a calculator to figure it out. But this really quick way to do it. All right. So so what we want to do is minus log of Ka. Well, let's do just quick uh, estimation. So instead of looking, what we're going to just look at is the exponents. So the pK is going to be the minus log of the exponents. All right. So this is going to be, so minus log of 10 to the minus fourth is 4. Minus log is 5, 8, and 10. Okay. All right. So pH. So this has a pH about 4, pH 5, pH 8, pH 10. So which one is closest to 7.5? Right here. Okay. And you could plug it in to see if it works out. All right. But, and it does. So the key things here is that the amount of acid in the conjugate base are equal. And therefore the pKa is equal to the pH. And the Henderson-Hasselbalch equation gave you that, but you know, you probably have tons of formulas in your brain. Okay, so here's that. So B and A are the same, so this is going to be 1. Log of 1 is 0, so this term gets rid of, so you can see that pH is equal to pKa. And then all you have to do is figure out the pKa from the Ka's. And if you know the pKa's, you know the pH. All right, so that's it for number 55. Okay, problem number 60. Actually, this is going to be a lot like the very first problem with the PCl5 going to PCl3 and Cl2. So so we have this equation. They're all the same state, so you don't have to worry about heterogeneity. Okay. What we're going to do is we're going to start out with a certain pressure of a reactant, and then we will have a final pressure after equilibrium. Okay. And so we're going to use that information to figure out the kPa. And so we're going to use the ice table. Okay. Okay, initial change equilibrium. Okay, so we start out with initial 1 atmosphere, 0 the products. This changes by some amount, and these both change by x, because the 1x, 1, 1, and 1, they all have 1 in front of them, so a geometry ratio. So at equilibrium, we get 1 minus x, x and x. So the total pressure, which is 1.2, has to equal 1 minus x plus x plus x. Okay, and well, we get 1.2 equals 1 minus x, or 1 plus x, and so x equals 0.2. Okay, so that means our reactant, there's 0.8, 1 minus 0.2. There's 0.2 of this, and there's 0.2 of our Cl2. So we know that Kp equals product 0.2 over times 0.2 all over the product, which is 0.8. And do the math, we get 0.05. Okay, and we can see that's B. Okay, so that finishes up. Take a good look at it, and we'll get it out to you, and you can look at it, and we can talk about it on Tuesday. All right, thanks.